the inspiration from this presentation sort of came from the work that I'm doing currently as a PhD candidate. So let me just talk about the focus of my PhD work first. I don't actually specialize in LLMs from from an official standpoint. So my PhD specialization, it deals with pathology. Pathology is sort of when you extract tissue samples from, a tumor or something like that, and then you put it under a microscope after staining with a special color to see certain things like cells, the shape of cells, things like blood vessels, necrosis, and then you try and make a diagnosis about what the disease is and stuff like that. Quite recently, or actually for a few years now, there's been this huge boom in sort of AI research for digital pathology, which is where you release samples and then you pass it into a scanner and then you digitize these slides. Often these files, these slides, they can be about 1.5 gigabytes to about 3 gigabytes to 4 gigabytes in size, depending on the resolution. They're very big files. And we've realized that, if you pass them to AI models, it's often possible to use certain features that you identify in pathology to predict things like what's the phenotype of a disease. How will it respond to certain treatments? Is there a survival probability? What's the survival probability? So on and so forth. So I focus on trying to derive those things using AI models applied to these tissue samples. Now, for my research to work, for all this to what we need at the base level is some sort of labels, for these images. So these slides that are scanned, we basically need the basic things like diagnosis. We need to know what location these tissue samples come from. Because location can tell us a lot about what the tissue sample is look like, what the cells should look like on a tissue sample. And then at an advanced level, we also need things like molecular findings. So what sort of molecular alterations caused this cancer to appear? Why is it being a certain way? So certain things like certain mutations can explain these things for us. And so we often need to derive these variables for us to train AI models effectively. Now the problem here is that when I arrived and I started doing my PhD, I was presented with information that looked like this. So for each tissue sample, instead of getting a nice set of labels presented in an Excel file or something like that, what I got was these free text pathology reports. So what happens in our hospital that I work at is that a pathologist speaks into a microphone and whatever they say is transcribed. So their observations regarding the tissue sample and all that stuff, that's basically transcribed from voice, and then it's recorded down. And so all that information that we need, the labels that we need, are encoded in these large bodies of free text. Of course, this is a synthetic example, but it pretty much represents what we see with pathology reports in our hospital. And this is a huge, it's a huge chunk of work for me to go through these reports one by one and obtain these labels from the pathology reports. Bits of information like the diagnosis, the mutations, those sort of things. If I went through those reports, I'd be dealing with about thousands of reports. Particularly because, with AI models, we train with about thousands of images, hundreds of thousands of images, too much work. So I had this idea at the start of my project. It was based on some work that I had done in my company before I started my PhD. I proposed that, why don't we throw these reports with some options into a large language model? Many of you are familiar with GPT, Google's Gemini or, Llama, whatsoever. But these are locally hosted LLMs, which means that instead of the LLMs being run on a server somewhere else, in a different country whatsoever, this is architecture, this is compute architecture that's only available for our hospital, or it's, the nationwide supercomputer or something like that. So this is a very enclosed environment, and we run the LLMs on this environment. So my idea was, why don't we pass these reports along with a set of instructions to extract these variables to the LLM so that we can easily obtain these labels that you see on the bottom right of the slide. Now, that somehow or the other, and I'll step back here because I think I'm covering a bit of the slide. that somehow or the other became a very popular line of research in the department. Everybody started pitching up on it. I think there was some research going on in the department already, but this sort of popularized LLMs. Uh, and now it's become sort of the prime focus of my research, at least, in this year. It seems like I'm already working towards a paper with regards to this, evaluating the performance of this extraction. So I often like to joke with my, supervisors and my fellow PhD colleagues that my PhD topics on images, but somehow or the other, I've ended up focusing on LLMs and jumping on this LLM hype that has emerged in the last few years, which is quite funny. But I mean, what we hope is that, we'll get this evaluation and whatever we are doing with LLMs now done by the final quarter of the year, and then we'll transit to working with the images with the extracted labels, of course. Um, but I think well, that is the impression, I think. But what I'd like to say is that when we're working with AI in medicine, we face a lot of interesting problems. Obviously, hospitals, they invest a lot in equipment, they invest a lot, in therapeutics and stuff like that. So it's not possible for us to whole of the most, the best compute resources, the infrastructure that Facebook or Google or, OpenAI are using to run their LLMs and things like that. It's not possible for us to do things like training my LLMs from scratch and stuff with the resources that we have. It will be very tough. We also work with limited amounts of annotated data. So let's say you're working on a rare tumor, like soft tissue tumors, which is my focus. That's a rare type of tumor, and then you get very limited amounts of data. We also struggle with things like data heterogeneity. Tumors, cancers themselves, the reason they're so hard to treat is because they are genetically heterogeneous. And so, that's something we also struggle with. Added to that, also have to adhere to very strong data privacy policies. So our pipelines, whatever that we put into practice, things like that, before they go into deployment, we need to make sure that these models do not compromise the security of our patient data at the hospital. And sometimes we have to work with the anonymized data, and we have to make sure that data is anonymized in the first place, so we're exposed to seeing things like patient information that's private. And the other thing, of course, as with any field, of course, it's very sensitive in medicine that performance requirements are adhered to, right? So clinicians are quite skeptical about the use of LLMs in practice, and to convince any clinician to adopt these in practice and all that, you have to show that these whatever output the model is releasing or something like that is accurate, or it's precise. It doesn't have a very negative impact on the patient outcome at the end of the day. So, these are some challenges that we deal with in the field of medicine. So, before I go into sort of talking about the practices with regards to LLM, at the end of the day, my goal is to sort of give you some practical insight into the use of LLMs, and maybe give you some insights into things I learned with regards to using them effectively. I thought I'd talk to you a little bit about where this, LLM sort of craze or this innovation appeared. For a very long time, there have been language models, and these language models have worked very well on somewhat, on a token level. And so the idea, quite recently, has always been to sort of embed these tokens in a certain vector space, and in that vector space, to try and correlate these words. So on the left, what you see is a sort of graph. Don't worry about the axis and the labels and all that stuff. Just worry about where these words are placed in the graph. Effectively, what an AI model is doing some sort of clustering algorithm. It's some sort of grouping algorithm to try and identify words that are similar. And for the longest period of time, AI models have basically been doing that. They group words that are related to each other to help them understand in a lexical context what these words mean. But recently, the challenge to finding out what these words mean in a certain context, in a certain sentence, by correlating words in the sentences, by giving them a certain sense of order, by paying attention to words that are very important. That feature didn't exist until I think about 2017 when people introduced this paper, attention is all we need. We did have models that were capable of dealing with sequential data, but they didn't do it that as well as models that exist today because of this paper. So this paper sort of introduced the transformer model, which kind of looks like this. So a transformer model basically takes an input sentence. What it does is it identifies the words in the sentences in a certain sequence. It tries to correlate them, and then it derives a sort of numerical representation, and it plays with this numerical representation to do different things. It can group sentences that are similar to each other. It can identify sentences that have a certain emotional sort of meaning, like, this sentence is derived from angry speech or, sad speech or something like that. You can do that sort of stuff. Or you can even use that numerical representation to output a new sentence, something like a translation. The thing is, this transformer architecture can be modified in certain ways to achieve these things. The transformer architecture consists of an encoder. So that encoder basically turns this text representation into some sort of numerical representation that conveys the meaning of the text. And then you can use this numerical representation to do whatever you want, like classification. You can even convert it to an image once you've converted it to a set of numbers. Or you can use a decoder, which takes the output from the encoder, which is a numerical representation, and then derives a different representation, which could be another language, for example. So in transformer architectures that are used for translation, the T5 models and all that stuff, basically they take some input text and then this text is basically used to guide an output and it's sort of transformation. But when we use an encoder-decoder model, the problem is that it's very limited to the content that's present in the text. The whole existence of this model is to ensure that that text representation that was provided, that original body of text, there is no deviation from that text. So any of the content in that text is translated, but none of that context one should be missing, and no context, no sort of content should be added to that body of text. But quite recently, people also realized that the decoder model could be used in isolation. And they realized that if you use something like a prompt, you pass something like an instruction or something like a question into this decoder model, you could basically get a generated token, and you could use that token to then generate another token and another token and another token, and eventually you would get a full response, a full sentence. What do I mean by this? Imagine that you have the question, what is the tumor? The AI model basically identifies the next most probable word. So it identifies whether or not, a certain, what sort of sentence would most be correlated with this input that was passed into the model. So based on a number of examples that it's seen, you may have seen this question, what is a tumor? You would have seen the answer, it follows a tumor is, something. And basically, this is called autoregressive generation. Effectively, when you look at ChatGPT and stuff like that, and you see that ChatGPT is basically generating a word by word by word response, it's effectively doing this autoregressive generation. It generates a new token, a new word. That word is added to the previous sentence, and that is passed to the model. It looks at that context, and then it identifies the next probable word, and then that's added, and then that sort of creates the sentence. When ChatGPT 3 was sort of released, you could actually see this this token by token generation because the model wasn't really fast then. But now it's so fast that you just see the output generated almost immediately. So yeah. No, prompts don't have to be trained in English. With the newer language models and all that stuff, you can use any sort of language, Dutch, Chinese, Tamil. There's a group in my previous company that's trying to train or fine-tune a model for Southeast Asian languages, things like that. So it's actually interesting. I would even say that with Chinese would be really interesting because I feel like Chinese is a different language in a sort of sense, right? With with English, you have words, and then those words are put into a sentence, and then sentence means something. But with Chinese, Japanese, some of these characters, like kanji and all that stuff, these characters themselves, they have their own meaning. So if you write a Chinese character, but you get some of the, a certain stroke character wrong, it can mean something totally different. So it's very interesting that an LLM can actually work on that language as well. So it's quite impressive. Um, but yeah, uh, I won't delve too deeply into the architecture because I'm here to talk more about the practical usage of LLMs. But just to discuss, the utilization of LLMs. In my practice, I've realized that there are a certain set of, parameters, a certain set of requirements if you want to get a good output from an LLM. The first is the instruction itself, and it's a lot more complex than people think. There are different techniques to prompt engineering that allows an LLM to perform better, even if it's not a very strong LLM per se. The other thing is the generation parameters, and I'll talk briefly about this later on. But there is this idea that there's this idea that the generation parameters affect the creativity of the model as well, and that creativity could have benefits. It could also have detriments in your use case. So let me just talk about prompt engineering. When you work with a large language model online, when you're speaking to an AI-based, support assistant, or when you're speaking to, ChatGPT, or when you're speaking to some LLM that's being posted online, what happens is that you interact with the model by providing a directive and a question, which is the thing that you see at the bottom. What you don't see, at the start is this whole idea of the system, the role of the model that has already been defined by the people that have programmed. Now, when we talk about prompt engineering, as I said before, when you interact with ChatGPT, you're basically providing a directive, an instruction, or you are asking a question. But you are not defining the system, the role, and you're not providing the examples that have been provided at the start. So prompt engineering is a lot more complex than people believe it is. Um, in fact, before you even provide this directive or input, that's passed to your travel agent online, that somebody was talking about an online girlfriend or boyfriend or something like that, before you even pass or even talk to those models, with every instruction that you pass, there is a very, very, very comprehensive set of instructions that have already been passed to the model. And if you want to ensure that your model is working effectively, these instructions are very important. So for a start, it's often important to provide the system, the role of the model to help it understand which context it's working in so it doesn't hallucinate beyond that context. It doesn't think beyond that context. It's important to define the task and objective, what you want the model to output, what you not want the model to output. And then it's important to identify and define a certain set of constraints and rules. Constraints like, I don't want you to provide any additional explanation, don't just give me the outputs. I'm only interested in a certain set of outputs. I don't want you to confuse me with your thought process or things like that. I don't want you to output this in another language. I don't want you to give those outputs in a different language per se. Those things are important because an LLM, when you're trying to give LLMs instructions, we thought that specific present age, maybe it might improve in the future for LLMs to perform, not to adhere to those instructions. And the next thing that people don't think about is the output format. Now, maybe it's not so important in this context, but often in the clinical context, when we're working with stuff, we often have to define something like a list, whether we want things in a table, whether we want things in a JSON format, like a dictionary, things like that. So it's very much important for us to be very specific about these things. And finally, we work with things like examples. So examples are annotated examples, things like what's the sample input, what's the sample outputs. It sounds simple, but it can alter the performance of the model very, very, very easily. Um, And so once those things are done, you could actually provide a set of instructions. And because these things have been happening in the background, because of this prompt engineering field that Phil said, would be a very good career, the last few years since ChatGPT was released, since these LLMs were released, it seems that a lot of startups have actually emerged, providing services like helping you decide on your shopping list, helping you with things like planning your vacation, travel and stuff like that. Um, and they come up with these they used to come up with these very impressive like, oh, our model does this, our model has this very strong architecture and all that stuff. It's capable of identifying this many destinations for you and stuff. It's basically just a set of instructions passed to an open AI server that's running ChatGPT, and that's basically what you're interacting with. And so it's a lot more impressive than it sounds. But what that also means is that it's a lot more accessible than it sounds, which means if you get access to an open AI, API like call, which is basically just a set of numbers that allows you to communicate with this open AI stuff. If you have basic understanding of things like Python coding, you could easily develop for yourself something like a travel agent, something like a research support assistant per se, or something like that. You could be creative. This accessibility has recently increased, with many more companies providing different API servers and stuff. Of course, security in that sense is a bit of a concern because they're not operating on your computer. You are basically communicating with the server, so you have to be careful about providing, information and stuff. But it's become very easy for us to develop our own AI applications quite recently. Um, Now, if you remember, I talked about this whole token by token, generation, and I don't have a lot of time to basically go through this, but I want to encourage you guys, if you have some time, maybe just go to Google and look up this thing called Transformer Explainer. Um, this was something that one of my colleagues actually shared with me. And so this transformer explainer actually shows you how sort of, models like ChatGPT, how these LLM models generate things on a token by token basis. Of course, there is a limit to the number of tokens that you can generate using the model. I think you can only generate a sentence of about, you know, words or something like that. But you can see how AI models predict what the next word in a sentence should be based on the existing words in a sentence. And these probabilities can be adjusted with different parameters like temperature, top P, and top K. So I encourage you to sort of look into this sort of how these tokens are generated and stuff. Why is this important? It's important because these parameters are also used in the adjustment and sort of the fine of AI models in terms of when it comes to their performance and stuff. If you play with these tokens and you increase the variable like temperature, what you would realize is that LLM starts talking a lot of nonsense. It's very much popular. It's very much possible that when you increase things like temperature, top P and top K and stuff, the LLM is effectively predicting probabilities of tokens from a very long list of possible words for a certain sentence. So the next word comes from a very, very, very long list of probable words. It's then taking the most probable words if the temperature is low and stuff. And if the temperature gets increased, the chances of it picking a word that's least probable is also very high. Somehow or the other, that will happen. And then it's very much possible that an LLM will start spouting gibberish. This is not just true for language models. It's also true for imaging models as well. But for you to see what this happens, I think you have to look at the transformer explainer and you have to see it interactively. Try playing with those parameters when you actually get access to an LLM model. If you're capable of using it in Python code and stuff like that, try identifying these parameters and try adjusting them to see how the LLM output basically changes. I feel like it's an interesting thing, but it's also the case that in papers, in research and all that stuff, many of the companies that release these LLM models have reported an optimal set of parameters and stuff. So when you obtain these models online and when you use these models in the field, if you find that the models aren't working well, one of the reasons could be that you're not using the optimal set of parameters for temperature, top P and top K. So this is something that we have to pay attention to as well. I'll explain why this is important in the prompt engineering examples as well. Um, and then there are advanced prompting techniques as well. So quite recently, this whole idea of prompt, chaining has been introduced, a sequence of prompts. So let's say, the objective of a deep learning model is to identify a certain set of diagnostic criteria from a report. Uh, but that diagnostic criteria is dependent on the previous thing that you extracted. So let's say, is this a brain tumor? Okay, if it is a brain tumor, I want you to find out which part of the brain it comes from. So that's a sort of chain, right, that you extract things from. And then from this part of the brain, which sort of, if it's the left brain versus the right brain, or is it, has the tumor diffused so much that it's now in the left and the right brain, you treat these things very differently. So um, prompt chaining, which is a sort of sequencing that's applied to extracting information from reports, the sequencing that's applied to LLM instructions, certain logic. This was also introduced quite recently. And what's really cool about this is that you don't have to ask LLMs questions in isolation anymore. You can now ask an LLM a question, and then your next question can depend on the answer from the first question and things like that. And that's actually reduced the amount of compute that's needed to extract a certain amount of information, because you can now tread a certain pathway and stuff. So quite recently, these advanced prompting techniques, prompt chaining is also something that was introduced very recently. And the other thing that was also introduced quite recently is a set of advanced prompting techniques called chain of thought, self-consistency, and tree of thought. So, if I want to look at certain reasoning, for certain outputs, which is, I don't know if you guys have used ChatGPT's reasoning feature, but quite recently, when I think ChatGPT version 4 was released, uh, there was a recent feature that was introduced where the LLM sort of thinks before it gives you an answer. So you would have noticed that if you didn't disable that feature, it would actually take you a longer time for it to derive an answer, because it goes through a certain chain of logic to obtain a certain answer. This very long, irritating thinking process that you would have to deal with an AI model is basically this sort of chain of thought or self-consistency or something like that. It's where the model looks at a certain sort of reasoning and a certain sort of, to try and give you an answer, a certain explanation. And then by using that temperature thing that we explained before, where it gets creative with different responses in a controlled fashion, it comes up with different possible answers. It samples those answers and then gives you the best answer or the most frequent answer, or it concatenates those answers and things like that. These advanced prompting techniques have recently improved the performance of AI models as well. So the important thing is that you know that these advanced prompting techniques exist and these prompting techniques are being developed. You don't need to know the intricacies of how these prompting techniques work. But why are they important? This is a graph from my study quite recently. We were basically performing this extraction and we were evaluating the performance of this extraction and all that stuff. I was working with a team of researchers from it, with regards to this sort of work. And what we found, we a large set of models on this data, basically 12 LLM models, everything from small models like 4 billion parameters and stuff like that, small models that are trained on smaller amounts of information and stuff like that, to the very large models that require a lot of compute that's normally not accessible to people, who have even the best gaming computers and stuff like that. So we experimented with all these sizes of models, these large models developed by Facebook, by these DeepSeek and all that stuff. And we compared it to the performance of the smaller models, like those the smaller DeepSeek version, Gamma that was released by Google and things like that. And we realized that beyond a certain point, beyond tiny models, which tiny models you can probably operate on a 4 gig GPU in your laptop. Beyond those models, any model that we use, the performance comparison, didn't reveal any change from a small model to a large model. What was more important was the prompting technique that we use with a certain model. So if you use the prompt graph approach, if you provide examples to the model, if you do your prompting correctly, our models could effectively, achieve a sort of 80% accuracy. So this is the sort of pit stop I'll take, and then I'll reset voice again. There we are. Am I back? Okay. Um, Thanks, Stephen. So uh, let's see. So the first lesson is sort of, ensure your prompting technique is correct. If your prompting technique is good enough, you don't really have to worry about the size of the model. But why is this important? It's important because the size of the model, isn't just something about, it's not just about accessibility. The large language models that are being used today consume, a large amount of electricity. It takes a lot of power to actually run these servers that allows you to generate outputs with ChatGPT, with DeepSeek, with Claude, what all these different LLMs that exist today. And if you're using a very large model, the amount of energy that's consumed, the amount of CO2 that's produced as a result, it's really huge compared to anything that's somewhat small. So a smart use of LLMs actually reduces the amount of CO2 that's released, for the amount of electricity that's generated to run these models. Um, I think that the use of LLMs, should be done in a smart sort of manner if they're going to be accessible to everyone in the future. Because the energy that they consume, the energy that's used to operate these models is really in excess. And um, there's actually a department within my workplace that actually looks at the environmental impact of the AI models that we develop, the AI models that we use. And people are actually very conscious of that in the modern day, that, the AI models that we use are not being used in excess. You may not need a very large model like GPT 5.0 or something like that to derive variables from a pathology report per se. You could use a smaller model and you could achieve a sufficient level of accuracy. In that case, why would you use something like a large model that runs on a lot of electricity when you can run it on your own servers and stuff? So picking the right model and then using an AI model responsibly is something I think that's not discussed excessively, but I think it's something that's very prevalent, something that's very important. There is a body of research that's dedicated to it, and for a sustainable future, I think it's something that we really should think about more often. The next thing is I don't know whether any of you have sort of used uh, have used LLMs on Hugging Face. Hugging Face is a website that basically allows you to download, get access to models that companies like Facebook, companies like Google, and all that have basically developed. This website, Hugging Face, allows you to download the weights of the model and to use them in your computer, or deploy them on your server, whatever. But you would have noticed that if you were looking up certain models, some of these models have something appended to them, something like instruct, something like medical fine tune, things like that. Fine tuning is one way of adapting a certain model to a task. Fine tuning is also something that basically allows us to adapt the style of the LLM to the context of use. So, for example, if you wanted an LLM to function as a travel agent, sorry about you reusing this travel agent example too much. If you wanted to use it in that context, you could fine tune an LLM to work in that context, basically by providing a bunch of examples of questions that people ask to a travel agent and then providing a sample set of answers. For fine tuning does not improve the performance of LLMs from a knowledge perspective. So imagine ChatGPT or your AI model that you're using was trained on a lot of information from websites that it scraped, regarding travel um, from maybe Japan. Fine tuning is not going to is not going to allow the model to provide insights on travel in China better than it was before. Fine tuning and providing examples is going to help the model obtain more knowledge with regards to different contexts from the context that it was trained on. Fine tuning is more about adapting the style of the model, to improve the model's outputs to tailor it to certain context. So I want it to be a better customer service, agent. I want it to be amicable. I want it to be friendly. I could fine tune the model by providing it more examples of that behavior. Does it improve the model's context, its knowledge and all that stuff, but improves the style of the model. And often in the medical field, we want the model to perform well in things like patient interaction, clinician interaction, derive, obtain certain results in a cleaner sort of fashion, present these results in a cleaner fashion, be succinct and stuff like that. We could provide examples and improve it in that way. So it's important to understand that fine tuning has certain limitations, even though it's quite popular these days with LoRa and all that stuff. Um, and the other thing that's become very important for us in the LLM sort of space is this thing called guardrails. So often, when we want LLM to interact with the patient, when we want the LLM to interact with the clinician, when we want to use it in a research context, one of the dangers that we have to deal with is sometimes the data that we use is not anonymized. Sorry. So you might things like a patient ID, their age, sometimes even their address in a report. And it's very important that we use algorithms, to identify these, things, these things like input IDs and stuff like that. So sometimes removing these IDs is not reliable enough for us to use an LLM that's capable of, doing many tasks to sort of remove these variables. Sometimes it's more effective, and this sort of that comment that Roy said about being hesitant about adding LLMs to all that stuff. Sometimes, it's the case that, when we want to do this anonymization and stuff, it's much safer for us to use a deterministic algorithm, something like identify 8 set of numbers that appear consecutively in the report. That's basically um, that's the patient ID. I want it removed or I want it replaced with something like XXXX and stuff like that. So having these guardrails before we pass the input to an LLM is sometimes um, is most of the time helpful because sometimes the data that we use is not really well anonymized and stuff. At the same time, the output from the LLM, if you've ever if you've ever worked with an AI model and then the AI model has said something, your input might violate our sort of, our sort of your input might violate our content policy or something like that. That's an input guardrail. Typically, the input guardrail telling you that if you pass something that sounds a bit toxic, something that sounds a bit explicit, and we don't want the AI model to process that, or we don't want the AI, you to see the output of the AI model. So a toxicity guard, hallucination guard, data leakage guard, things like that. This is the kind of pre-processing and post-processing that we often have to develop when we talk about AI models in the medical field. And finally, I want to talk about running large language models on small systems. So quite recently, I think there are different AI companies that introduce models that are very small in size. So Quen, which is the model that was developed by Alibaba, that's an LLM. They released a version 3.5 for their model in 4 billion parameters. And my work laptop, my company's laptop, has a 4 GB GPU. So a 4 GB GPU is a graphics processing unit. That's the stuff that basically makes SL look very nice. That's the stuff that basically allows you to play video games and stuff like that. A 4 GB GPU is probably half the amount of video memory that you would find in a gaming laptop. So for most of you who are probably working with gaming laptops in this room right now. Many of you will probably have GPUs with about 6 GB or 8 GB of VRAM. Some of you might even have 12, 24, depending on how much money you spend on your piece. Um, these GPUs are presently capable of running the newer releases of AI models from companies like Quen. And I was really impressed that, these large language models that were so inaccessible to us in the past have been compressed in such a fashion, to, that they're capable of running on such small systems. However, it's also become possible for us in recent years to use AI models that have been developed on very powerful computers. And one of those methods is quantization. So for you to understand quantization, it's important for you to understand how a deep learning model is trained. I will not explain that excessively in this lecture, but I will encourage you to look up my lectures at the Science Circle on computer vision or deep learning per se. I basically talked about how deep learning models are trained. Basically, what a deep learning model is doing is converting an input like a body of text or an image to a very long set of numbers, and then it's correlating the numbers with an output like a classification or some other text, or some other numerical representation with some multiples called weights. And these weights are typically very small. Why are they very small? Because for the computer to effectively update its weights in an effective manner that allows it to learn, that allows it to improve the relationships between multiples and the input variables, it basically has to use this thing called a learning rate. And the smaller the learning rate, the slower the updates take and all that stuff. But the larger the is the AI model doesn't learn very well. What you end up with is this thing called a gradient explosion. Um, so to this, you could sort of compare this to imagine you are a dancer. You're new to dance, and you've started, you've just started learning dance. You've just started going for classes. You could learn things about 3 to 4 steps at a time, but imagine that you started learning things about 12 steps at a time. What could happen is that, instead of learning things very quickly, you start getting very confused. Your dancing starts getting very messy. And then you start jumping back and forth and you get very discouraged because you can't really learn these steps properly. So then you realize that you have to start learning steps, these steps to for a dance move at a very um, the short space, maybe about 3 steps, 4 steps. I'm going to move my left hand here, my right hand, it goes here, and then that's enough for now. I'll do that and then I'll repeat like that. It works the same way with an AI model. So when it comes to the learning rate for an AI model, something that's a bit too small. If you have a learning rate that's too small, sometimes you get this thing called a vanishing gradient. If you have a learning rate that's too high, then what you get is this thing called gradient explosion. It doesn't really learn. So this training process has to be very precise, but that doesn't necessarily mean that it inference, when you're using the AI model, this trained model needs the same level of precision. Essentially, the more decimal places you need, for these variables, these numbers represent the words and all that you've input into the computer, the more memory you need. The more memory you need to use, more memory you need in your GPU, the more memory you need in your RAM and all that stuff. And then sometimes you're not capable of running the really small systems like your laptop. But having trained the model on a very powerful system in a server somewhere else, you could then deploy these models with quantization, which is to reduce the precision of the model to reduce the amount of decimal places to basically round these weights up to a certain number and all that stuff. And just by doing that, the amount of the amount of memory that these numbers then consume on your computer is then much less. The amount of memory that these things consume on your VRAM, your GPU, is actually reduced quite heavily. Because of that, you're capable of running it on your laptop. Granted, when you run these systems with quantization, there is a small reduction in the level of performance. But quantization is one way to achieve a reasonable level of performance on a very small system. It's worked for us in quite a few contexts in the medical field, whether it's dealing with text data or imaging data. We've been able to run some very, very powerful models at lower precision with a reasonable level of accuracy as well. So yeah, it's something that we experiment with. So yeah, this has been a few sort of insights that I've sort of thrown at you from my experience of working with these AI models in medicine. I feel that there's something that my dance instructor likes to say about learning to be more creative in dancing. Um, if you want to be more creative in dancing, work in a box. So let's say I dance partner dancing. It's called West Coast. And in partner dancing, often it's the case that with leaders, especially new leaders, we like to try a lot of moves because we feel like when we dance with followers, without many moves, we're kind of boring. Um, and so we throw a lot of these moves that we've learned in classes and stuff like that, and we throw them one by one by one by one. Um, but we actually ruin the dance that way by throwing these moves because we're not being very with anything new. And so something very inspiring that my dance instructor told me one day was, limit yourself to a certain set of moves and tell yourself, maybe I'm only going to do 4 moves in this dance today. And when you do that, and when you force yourself to do that, suddenly you have to think about how you can manipulate those moves to make it look more interesting. Can I use shoulder isolations? Can I pop my body this way or that way, or move my body in a certain way to make it look very interesting? In that same way, um, in the medical field, we deal with a lot of restraints. We deal with, smaller systems. We deal with patient privacy. We deal with things like, safety and all that stuff. And all of these constraints basically exist for us. And it's because of that box that we find ourselves in that we have to find creative ways of using models to, achieve the results that we want. And I agree, sometimes it's not just a matter of using LLMs. Sometimes it's about using encoder decoder models. Sometimes it's about using code. Sometimes it's about coming up with these solutions and amalgamating them in ways that people haven't thought about before. And that adversity in our field, those challenges in our field, I think makes us, uh, makes us better, makes us better scientists in a certain way, makes us better developers, makes us better engineers. So I feel like um, if if you decide if you're working with LLMs or whether or not you're working with AI, working with something else, I encourage you to find challenging ways or restraints to work with these models sustainably, to work with these models better, and to find creative ways to use these models because those innovations will probably be very important to human society in coming years and the coming generations as well. So yeah, that's my presentation. Thank you very much.